Hello, everyone. Welcome to our course, Machine Control Systems. And in this course, we were studying our chapter number 7, which is Root Locus. And we were discussing for the part 1, Root Locus Sketch. And this is the second lecture of Root Locus Sketch, in which we are studying root rules to sketch a root locus. And in the previous lecture, we have already seen that how a root locus is defined and how a root locus starts or initiates from a pole and terminates to the zero. And we have later seen the foundation towards why we used to do that, for the very simple reason we have discussed the analytical foundation behind it, which shows us that when k was equals to 0, that means when you and I were starting the root locus, right? So the values of roots were closest to the poles, right? Right here. And as we move from k equals to 0 to k equals to infinite, right? So the root locus was about to end at this point from k equals to 0 to k equals to infinite. And when k was equals to infinite, the values of roots were closest to the zeros. That's why we sketched the direction of root locus from poles to zeros, that is from k equals to 0 to k equals to infinite, which is start of the root locus to end of the root locus. We also discussed why we did that, because at k equals to 0 the poles were dominant, and that is for the reason why our roots were at the place of our at the position of our poles, and um, at k equals to infinite the zeros were dominant analytically. We have demonstrated that before. So in that way, the roots were lying towards the zeros when k was approaches to infinity, or you can say we're about to end the root locus, right? So that was the case. If you need to recall any of these, please feel free to revisit the previous lecture and catch up with us. We also discussed some other features. Let's say if we have some roots, some poles which do not have any zero pairs, or let's say we have two poles and one zero, so we will assume that the pair of zero associated with this pole is at infinity. So we'll assume that this zero is at infinity, which is paired up with this pole, and that's why the direction of root locus will be from pole to the infinite zero, which is hypothetically present at infinite. Similarly, for the case when we have a two zeros and one pole, so we'll assume that the corresponding pole pair for this zero is at infinity, and that's why this root locus is starting from that pole and reaching to the end of root locus to this zero, right? So yeah, we have already this is just a quick recap for what we have done so far in the last lecture. So this was our rule number 1, and that's it for rule number 1. Now we'll move ahead for rule number 2, and let's see what's there for us. So yeah, rule number 2 says that the real axis to the left of an odd number of an open loop pole and 0 is part of the real axis. So do not get confused with too much complexity on the slide. It's quite simple, as whenever you have an odd number of open loop poles and zeros. So let's demonstrate it using this example. We have a plant function, which is this plant function, and by equating the denominator with 0, I'll get the poles, right? So we can already see that there are 1 and 2 and 2. We have 5 number of poles And if I have equate the numerator with 0, I will get 3 poles. That is 1 and 2 from here, so I can have 3 zeros and 2 poles. And of course the difference between the number of poles and numbers of zeros are the missing number of zeros at infinite. So if the difference, whatever the difference is, that amount of poles and zeros are present at infinite. So that's rule number one. We have already discussed this concept in rule number one. And so far, here comes the rule number two, which says that whenever you have a odd number of poles, right? So when number of poles is greater than number of zeros, and you can say the number of poles is odd, so you can say that the real axis on the left is part of the root locus. So you can already see that, right? So this is more like a demonstrative sort of rule, not primarily you can use it, but yeah, it's an observational rule. So of course let's see how can we draw this. So let's say if I have 5 poles, so I draw 5 poles here, whatever their positions are, and now I'll try to decide with every pole I associate them with one of the zeros, and I attach this pole with this zero, this pole with this zero, and this pole with this zero. And these two poles were the residue poles, and I will say that both of these poles are approaching to their corresponding zeros at infinite. And by saying that, um, uh, please do not get confused with, for now at least, the directions of this root locus, right? So we will be discussing in the next rules how, why, the 2 points, number one, which uh, pairing, right? So which pole to associate with which zero. So pole zero pair will be discussed in the next rule. And the second rule is the direction and points, right? So you can see these points, these asymptotes, right? So you can see that this pole is moving towards a certain point, and then it's moving toward upwards towards the infinity, and this pole is moving towards this point, and it's moving towards the downward towards the infinity. Let's call this point, um, we call this point break away point, right? And we can find this breakaway point independently as well as with reference to centroid. So what is the centroid for? This is basically centroid um, for asymptotes, right? So we'll discuss this, what is asymptotes are and why we are using it. One more thing we are interested in, and we do not know right now, and we won't be discussing in this rule, is that what is this point, right? So we don't know, either these poles connect to each other at this point, or maybe this point, or let's say this point. So you might ask, you have some questions, why to choose this point. So this is actually your breakaway point, and you'll be choosing it on the basis of your centroid. And we'll see how to select this breakaway point in rule number 6, and how to um, find the centroid, which is somewhere like here. So in rule number 3, we'll see how to calculate the centroid. And also you might be interested that what would be the angles, right? So let's say this is your alpha 1, right? And this might be your alpha 2. So you might be interested at what angles these root locus would take off and away from this breakaway point. So you also need to find these angles. So you also need to find out angles of these asymptotes, right? So these whole centroidal angles would be covered in rule number 3, and the breakaway point, the location of the breakaway point, will be covered in uh, 6, rule number 6. So don't get worried. The purpose of discussing all of this is because there might be questions. Number one, about which pair to select, with which pole is to be paired with which zero, and number one, what is the direction related to directions, right? So this whole theory was about the directions, right? So oh, as I said, that the pair, how the pair is selected, and how the breakaway point, centroid, and angles are selected would be covered in the upcoming rules. However, the only thing we want to demonstrate here in rule number 2 was that whenever you have an odd number of poles, and number of poles is greater than number of zeros, so you can see that your real your real axis to the left would be part of your root locus. Yeah, so you can see that. So that's the common observation here, and that's here to demonstrate. We'll see some of the similar examples, so to emphasize and reinforce what we meant by rule number 2 here. So let's see one more example. And in this example, we can see that we have, let's say, s equals to 0 here. So we have 0 comma 0 comma minus 3. We have three poles here, and with three poles we can't see any zeros, and we will assume that np is equals to 3, and number of poles are 0, so we'll get 3 as np minus nz, which demonstrate that three zeros are present at infinite, hypothetically, yes. And again, we will place such in such a way that one pole would get attracted to the 1 infinity, 0 at infinity, and another two poles which are coincident and would be connected to uh, root locus heading towards infinity, towards their respective poles. So yeah, again you would have the same question, that why we choose these directions, like, so what is the directions, why this direction for this one, and why this direction. So again, this will be covered in rule number 3, and for breakoff point, right, this would be covered in 6. So do not worry about um, your directions. Although there is one more interesting question which I want to address at this point, and which is that why cannot we connect directly to the infinity overlapping this line? So that's against the rule, right? So we want to be very careful that if I want to connect some pole with some zeros, so I have to be very careful that this root locus, number one, do not intersect with any other root locus, and do not intersect with any other pole or any other zeros. So it should be very distinctive, that it does not pass through any poles or zeros apart from the pole pair for which it has been generated for, and also it does not intersect with the any other root locus. So root locus do not intersect with itself as well as with any other root locus. So hypothetically you can say that, oh, okay, so of course these root locus are actually crossing each other, so this is an approximation. So you can say that these seem to be touching each other, but to be approximate result, they are, yes, they are touching, but not exactly, they're not touching each other, right? So we can say that, or you can say that they meet at this point and they depart from this point. uh, yeah, to make it simple, yes, this is an analogical rule, so that's why there are some issues to which will be addressed in partial forms. Yeah, so that's it. And the observation for this rule is also that we have three number of poles here, and for this reason, which is an odd number, we have np equals to odd, and number of poles is greater than number of zeros. So we have the left half real axis, left half, not half, it's the real axis to the left would be part of your root locus. So it's also demonstrated here, right? So it's also demonstrated It's part of root locus when poles and zeros are odd. So do not worry about the directions, and we'll be seeing it very soon. Right? Let's go for the final example, and let's a bit maybe a little bit tricky for you, but do not worry about it. It's not that tricky, but the point is we want to just demonstrate rule number 2 here. So if you see, of course I can join this if I haven't drawn this root locus before for this plant function, let's say. So if for this plant function we have two number of poles at -1 and at -2, right? So these two number of poles are present here, and the number of zeros would be s equals to -3. So one zeros. So of course I can say that np minus n1 would be equals to 2 minus 1, which would be equals to 1, and there would be 1 0 at infinite, and of course 1 0 is present here. So if I draw a 0 and 2 poles at their respective positions, I could directly join this pole with the 0. But the question is, if I join this pole with the 0, how I am going to be able to join this pole to this pole at infinite, right? So I have to either overlap these pole pair, which is not a condition, because I cannot, by principle and by rules, I cannot, a root locus cannot intersect with any other poles and zeros irrespective of its pole pair, and also it cannot not cut or intersects through any other root locus. So that's not the case. So maybe you can say that, okay, so we can directly connect this pole with let's say, let me to on with the laser, and this pole, let's connect this pole with this 0. And how about if we make this pole come here and make a round trip here and then went to the infinity? But that's also not possible, because it's not possible for a pole to change direction like this. In order to have a break-off point, it must have two poles coming up to a break-off, single break-off point, and then breaking off towards it. So it is not possible for a single pole to come up to a break-off point and break away to some other values and break into some other point, right? So this point is actually your break away point, right? Because in here the root locus is coming to this point and leaving outside the axes, right? So at this point the root locus is leaving the real axis. So the point at which the root locus leaves the real axis is called actually your breakaway point. And the point at which the root locus collects to a single point on the real axis is called break-in point, right? So this is your break-in point where root locus is collecting in, and this is your break-off point where root locus is uh, departing, or you can say splitting away, right? So we'll have formal definition for these breakaway and break-in points, just to uh, reinforce. I am repeating this. So in order to have a pole to collect at a breakaway point and split away, depart away to some other values and break into some other values, right? You must have two poles, right? So it's mathematically demonstrated that you want to have two poles to be connected, right? So a single pole cannot jump through these pole pair and go to infinity, right? So in order to have, we have to have a smart solution in which that these two poles collect together here, and one pole went to this break-in point, another pole to the same break-in points, and one of the pole gets back to the 0, which it could go directly, and the other 0, which is uh, jumping away from this breakaway point and to this break-in point, would go to the infinity. The one of the pole is going round trip to the 0, local 0, and one of the pole going to the round trip to the 0 at your infinity. So yeah, that's the simple rule. So only one thing to be is left to here to be discussed, which is the shape, which is the circle. So do not get worried about the shape still. But of course, I won't say that we would be covering in our some of the rules that how it's going to be a circle, because that's quite beyond the scope of our of this course. But as a matter of you can say analysis, I can give you an example that when you make two lines before, like you were like, let's say these were two examples, and you can say these were parts of a hyperbola because they were in asymptotes, you can say, because these if we will be going to the next rule, so these lines would be drawn as a result of the asymptotes. And we remember when we were drawing the asymptotes, this was actually the nape of a hyperbola. So for hyperbola, you remember that the eccentricity was greater than 1, and if somehow something happens and the eccentricity gets equals to 1, so this is not more anymore a hyperbola, and this is your circle. And that's why we are having a circle here. But unfortunately, we cannot go into further detail why it's a circle, but you have to think in a way that whenever you see this case, in such a way, when np is greater than nz and number of poles are greater than number of zeros and number of poles are even, so there must be a circle drawing up here, and in which you can say the one of the pole zeros would be at the center of the circle, and the distance would be from first pole to 0 would be a, and pole to pole distance would be b, and you can calculate the radius of the circle using this. So whenever you see this structure, you will construct a circle with the corresponding radius by calculating the distance between them. So it's not that difficult, right? So so I have also written that in descriptive form. You can also read that, why is that. So yeah, to keep it simple, this is to the far we can go, and you can further read about it, why it's a circle, and how what makes this eccentricity to leads to 1. So uh, yeah, so that's, I think, enough for this example. We don't need to go into any further details for now, at least. Yeah, for the scope. All right, rule number 3. So in rule number 3, as I discussed, what we were about to discuss was the centroid. So we were interested in calculating the centroid, and we were also interested in calculating the angles of the asymptotes, right? So we are interested to find two things, which is the angles of the asymptotes and the centroid. So let's us deal with the formulas, and we can see the np minus nz. We are always familiar with this ratio, this difference, and we can calculate it for any transfer function we want. And then we'll put different values of I to find out different angles of asymptotes which are present in that root locus. Similarly, for centroids, the easy way to calculate is sum of the all poles minus sum of all zeros divided by n pi minus nz. And as a result, what you will be getting would be a number or a fraction, whatever it is, and that would be the location of your centroid on the negative real axis. So let's demonstrate this by means of an example. And we have this example in which we have two poles at -1 repeated poles and one pole at -6. So we have three numbers of pole in total, and we have, of course, we do not have a physical pole here, physical zero here, so we can assume or hypothesize that there are three number zeros at infinity. So let's draw a sketch for this. Before I draw a sketch for this, of course, now I am concerned in rule 3, what is the shape and what is the structure, right? So I am concerned about the angles. So first calculate the angles using 2i plus 1 pi divided by 3. This is the formula for asymptote, angle of asymptotes, right? So when I put I equals to 0, so I get pi by 3, then I equals to 1 gets pi, and then I equals 2, I get 5 pi by 3, which is uh, 5 by 3 is 60, and 5, it would be 300 degrees, right? So let me write it in degrees just for your um, convenience. So let's say this is your 60 degrees, and this would be your 180 degrees, and this would be 300 degrees, right? And if I say this, let's say if I the 7 pi by 3, I'm not taking 7 pi by 3 because this is exactly the same angle as 1, and I think that's quite obvious. If you add pi by 3, add a 2 pi, so you would get actually 7 pi by 3, which means that this is exactly the same angle. These are, so no need to take it again, because this again the pi by 3 by after one rotation. So we will neglect these values and onwards all values, because that would be like repeating again and again. So these are three distinctive angles which for the asymptotes: 60, 180 and 300. Or you can say 300 is also called minus 60 degrees from the positive real axis, from the real axis, I'm sorry. And for the intersection point, which we call as centroid, we calculated the sum of all the poles, which is -1 plus -1 plus -6, and there are no zeros, so that's why we do not included any physical zeros here, and we sum up here, and -8 by 3 shows your location of your centroid, sorry, on your real axis, negative real axis. So here you can see again that we have two asymptotes drawn at 60 degrees and minus 60 degrees, and one of the asymptote, or you can angle, you can say, is at 180 degrees. So it's quite obvious. Now you can select. The question was how to select a pole pair, right? So this was our question in the last rule, which was making us curious, that how to select a pole pair. So it's quite simple, it's common sense. If you have one asymptote at 180 degree, which means that none of these pair can be going to 180 degrees, because that would coincide with this pole. So of course this pole would be going towards the hypothetical zero at infinity, and that's how I will check this angle 180 degree. I obtain it from here, 180 degrees from here, and remaining two angles, which were 60 degrees and minus 60 degrees, or you can say 300 degrees, right? So you can find it like 60 degrees and minus 60 degrees and draw those asymptotes, and with reference to those asymptotes you draw the root locus, with this point as your break away point, right? And of course the break, these both of the roots lies on this root locus. So one root goes to this mark and other goes to the opposite mark, such that both of these root locus touches the asymptotes at infinity, and that's exactly the definition of an asymptote, right? So no need to confuse. So now we already know. Now congratulations, you know how to select an angle and how to select a centroid, right? So this is your centroid C. So by reference of your centroid, you have a breakaway point, and with reference to that, you can sketch your root locus, and the other part is your angles. And you, once you have figured out the angles, you can select the pole pairs, and once you figured out the angles, so you can collectively, with angles and with centroid, you can collectively find the directions, right? So yeah, so you deal with both of these points, right? So which were a question in the previous row. So let's reinforce this concept by a few more examples. So let's say this is our example. In this example, we have two number of poles here and one number of poles here, so it makes three poles. Uh, so we have three number of poles here, and we have just one zero here, so we have one zero here. So np minus n was the 3 minus 1 would be equals to 2, and we have hypothetical two zeros at infinity. So let's sketch that. Before sketching that, I can write the formula that which was 2i plus 1 times pi divided by 3 for angles, right? So for asymptote angles, I'll consider I equals to 0, 1, and so on. So I can see that, and unlike the last case, I can see after the two angles, the angles get repeated. So I don't need to take any more further angles beyond 3 pi by 2. So it's obviously it's 90 degrees and one at 270 degrees, right? So these are like opposite to each other, one going upward and other going to the downward side, right, of the plane. And I can simply find the centroid or the intersect using the same formula, that sum of the poles and sum of the zeros divided by the total number of np minus nz, which was equals to 2. And I can further split these into uh, now I can find the location of poles, and I'll sketch these simply by simple technique in which I know that if these are two angles 90 and 190, so these will be the two asymptotes uh, for two of the poles, like 90 and minus 90, or you can say 2 pi 3 pi by 2. And from these two poles you can see that this these poles would be approaching towards the infinite, touching intersecting the asymptotes and infinite, right? So in that way you can sketch these asymptotes, and the residue pole will be connected or will be fed to the zero, local zero, right? So that's how you connect it, and that would be your root locus sketch for such graphs, right? So I don't think we have any confusion regarding. It's quite simple, right? So that comes up with a simple problem in which we have, which is your actually assignment. So I might not interfere with this part. Yeah, let me help you a little bit with this. So I can say that how many poles are there? We have np equals to, what is that, 3, right? So we have minus 2, minus 4, and minus 6 here, and I have np equals 3. And what about nz? Is it's 0, so I can calculate the ratio. Then by np minus nz I can calculate the values of angles and the values of centroid. And once I know that, I know the pair poles, which pole to connect with which pair of 0, right? And by using centroided angles I can find the directions. So I think we have complete picture to sketch a root locus, right? So that's quite it for lecture number 2 of chapter number 7a, sketching the root locus, and we'll see you in the next lecture.